Welcome back to the deep dive. Today, we're tackling something a bit unusual. We're not just exploring a science topic, but actually, like the blueprint for an AI designed to help us understand it.
Exactly. It's like looking under the hood of a new tool meant to unlock deeper insights.
Yeah, pulling back the curtain. And this AI, it's specifically for general chemistry.
Right. Tailored for a community college course using what's called an atoms first approach. The whole idea is to give a chemistry professor a sort of um, AI assistant, something that helps them dig into the material, figure out where students might get tripped up, common misconceptions.
Oh, anticipating the problems.
Precisely. And then develop maybe some new ways to teach tricky subjects. Today's focus is liquids and solids.
Mm. And our sources for this are pretty unique too. We've got the actual prompt, like the instructions, for this Notebook LM General Chemistry Deep Dive Assistant. And we're pairing that with the textbook material, Chapter 12 from Chemistry, Atoms First, on liquids and solids, plus the lecture slides that go with it.
hmm So the AI, when it first analyzes this stuff, it would immediately flag intermolecular forces. That's the key.
The core concept. Okay, let's unpack this. So fundamentally, this AI is meant to be like an expert tutor, right? Or maybe a study partner for the professor.
Yeah, exactly. Providing insightful patient guidance. But it's more than just answering questions. It has to understand the context.
Which is that community college setting.
Right. In Oregon, running on a three-term system, fall, winter, spring. So the material needs to be, accessible, foundational. It's really about building strong concepts first, not just jumping into complex math.
Gotcha. So less calculation, more understanding why.
Exactly. And that AI is built to be proactive, to suggest things like, hey, maybe explain it this way, or here's a tricky question to ask.
Mm-hmm.
And crucially, it's that misconception identifier function, helping the professor see potential confusion before it happens in the classroom.
That sounds incredibly useful. Okay, so keeping those AI goals in mind, let's dive into the actual chemistry of liquids and solids. How would the AI start breaking this down?
Well, like we said, it starts with intermolecular forces, IMFs. The AI would definitely emphasize that these are the absolute key. They explain why stuff is solid, liquid, or gas. They dictate all those physical properties we see.
Right. I mean, gases, we sort of ignore IMFs. Particles are just flying around super far apart.
Pretty much negligible, yeah.
But liquids and solids, they're the condensed phases. The IMFs are strong enough to hold things together, keep particles close. Visually, you picture gas particles way spread out, liquids close but sliding past each other.
Like that crowded dance floor analogy you used.
Yeah. And solids are just, well, stuck. Vibrating, but stuck in place.
And the AI would stress that it's the differences in the strength of these IMFs that explain everything else. Surface tension, viscosity, boiling point, all of it.
Okay, so starting with liquids then, how do IMFs show up there? The AI zooms in on surface tension first.
Yeah, that's a great place to start. Surface tension is basically the energy needed to stretch out a liquid surface.
And this is where it connects directly back to IMF's stronger forces, higher surface tension, like water.
Exactly. Water's hydrogen bonds are super strong, giving it that high surface tension. You see it beat up, or how those little water strider insects can walk on it.
So why does that happen, that beating up?
It's about the forces. A molecule inside the liquid gets pulled evenly by neighbors all around it, but a molecule at the surface doesn't have anything above it. So the net pull is inward. It pulls the surface molecules tighter, minimizing the surface area, creating that sort of skin.
Ah, okay. And that explains the meniscus too, that curve in a tube.
Precisely. It's a balance between cohesion molecules attracting each other and adhesion molecules attracting the container walls. For water and glass, adhesion wins. The water climbs the glass a bit, making that concave U-shape.
But mercury's the opposite.
Right. Mercury atoms stick to each other more strongly than a glass, so cohesion wins, and you get a convex shape, bulging upwards. And capillary action, like drawing blood into a thin tube, that's mostly adhesion pulling the liquid up. The AI would definitely highlight these, maybe suggest visuals or demos to show that balance of forces.
Makes sense. Okay, what about viscosity? That's another liquid property.
Viscosity, yeah. It's just the resistance to flow. High viscosity means it flows slowly.
Like molasses. Or cold honey.
Perfect examples. And again, it ties back to IMFs. Stronger forces mean higher viscosity. The textbook example, glycerol, C3H8O3, is a really good one. It had 3 OH groups.
3. Wow, so lots of hydrogen bonding potential.
Huge potential. But the AI might also point out it's not just the H bonding. The shape matters too. Glycerol molecules are kind of bulky and can get tangled up.
Ah, like molecular spaghetti?
Sort of. That entanglement adds to the resistance to flow. So the AI might suggest asking students why glycerol is so viscous, pushing them beyond just counting H-bonds to think about shape as well.
Interesting. Okay, moving on. Vapor pressure and boiling point.
Right. So liquids evaporate, right, turn into gas. That's vaporization. The reverse is condensation.
And in a closed container, they reach equilibrium.
Exactly. Dynamic equilibrium. The rate of evaporation equals the rate of condensation. Vapor pressure is the pressure exerted by that gas above the liquid at equilibrium.
And things that evaporate easily, like rubbing alcohol, are called volatile.
Yep, high vapor pressure. And vapor pressure goes up with temperature. Always.
Because more molecules have enough energy to escape.
Precisely. More kinetic energy to overcome those IMFs, holding them in the liquid. There's an equation for this, right?
Yeah, the Clausius-Clapeyron equation looks a bit intimidating.
It can, yeah. But the AI would break it down. It basically just mathematically relates vapor pressure to temperature. If you know the pressure at one temp, you can calculate it at another.
And that diethyl ether example, worked example 12.1, seems key, especially that think about it part.
Absolutely crucial. The AI would flag that. Does the answer make sense? Vapor pressure must increase with temperature. If your calculation shows it decreasing, you messed up somewhere.
It's a sanity check. Easy to skip if you're just plugging numbers.
Very easy. And that's a common student error the AI is designed to help the professor anticipate and address. It's about building that critical thinking.
Okay, so how does vapor pressure connect to boiling?
Boiling happens when the liquid's vapor pressure equals the external pressure pushing down on it, usually atmospheric pressure.
Which is why water boils at a lower temperature up a mountain, less atmospheric pressure.
Exactly. And the punchline, again, is IMFs. Stronger IMFs mean lower vapor pressure at a given temperature, which means you need a higher temperature to reach boiling, higher boiling point.
It all circles back to those intermolecular forces.
Always. That's the unifying theme the AI would constantly reinforce.
Okay, let's shift gears to solids. IMFs are even more dominant here, locking everything in place.
Right. And that leads directly to the melting point, the temperature where particles get enough energy to break free from that fixed lattice.
So stronger IMFs.
Higher melting point, exactly. You can see that really clearly looking at trends, like how water's melting point is way higher than expected for its size because of hydrogen bonding.
Do solids have vapor pressure too? I mean, does ice evaporate?
It does. It's called sublimation solid directly to gas. Usually the vapor pressure of solids is very low, but there are exceptions. Mothballs, that naphthalene smell, that's sublimation. Iodine crystals do it too. And dry ice, solid CO2, has a huge vapor pressure at room temp.
Wow, over 56 atmospheres. No wonder it sublimes so readily.
Yeah, it doesn't hang around as a solid unless it's really cold or under pressure. Structurally, though, solids mainly fall into two camps, amorphous and crystalline.
Amorphous is like disordered glass.
Yeah, glass is the classic example. No long-range repeating pattern.
Yeah.
Often forms when liquids cool too fast to get organized. Crystalline solids, on the other hand, have that perfect repeating 3D structure. Most solids are crystalline.
Like salt or sugar or metals.
Exactly. And that repeating structure is built from a basic unit called a unit cell.
Okay, unit cells, I remember simple cubic, body-centered cubic, face-centered cubic.
Those are the key ones for introductory chem, yeah. The AI would focus there. Simple cubic, DCC, body-centered, BCC, face-centered, FCC. What's important is the coordination number. How many neighbors each atom touches? 6 for CC, 8 for BCC, 12 for FCC. And how the atoms are shared.
Right, because an atom at a corner is part of 8 cells, on an edge is 4, on a face is 2.
Correct. So you calculate the net number of atoms inside one unit cell. 1 for simple cubic, 2 for BCC, 4 for FCC.
And that relates to how tightly packed they are?
Yes, leading to the most efficient ways to pack spheres, called closest packing. Face-centered cubic is one type of closest packing. These structures have that coordination number of 12.
And we can use this, like that gold example, calculating its atomic radius from its density and the fact it's face-centered cubic.
Precisely. Worked example 12.2. You relate the macroscopic density to the microscopic arrangement. And again, think about it. Check atomic radii are usually around 1 angstrom. Does your answer fit? The AI would emphasize linking these micro and macro views.
Okay, so within crystalline solids, there are different types based on what's holding them together.
Exactly. 4 main types the AI would help distinguish. First, ionic crystals.
Like salt, NaCl, positive and negative ions.
Yep. Held by strong electrostatic forces, high melting points, hard, brittle. Poor conductors as solids, but good conductors when melted because the ions can move.
Okay.
Covalent crystals, or network covalent solids. Think diamond or quartz. Here, atoms are linked by a huge network of covalent bonds.
So they're super strong.
Very strong, very high melting points. Diamond is the hardest known substance. Graphite is interesting, also carbon, but in layers. Strong bonds within layers, weaker forces between them makes it slippery, and it conducts electricity.
Third type?
Molecular crystals. Here, the lattice points have whole molecules, held together by those weaker intermolecular forces we started with, van der Waals forces, maybe hydrogen bonds.
It's like ice, or dry ice, or sugar.
Ice, dry ice, iodine, sugar.
Yeah.
Because the forces between molecules are weaker, they tend to have low melting points and are softer.
Yeah.
Ice's structure, specifically, is key. Hydrogen bonding creates gaps, making it less dense than water. The AI would definitely stress that anomaly.
Super important for fish. And the last type?
Metallic crystals. Metal atoms packed together, typically in BCC or FCC structures. The bonding is unique, a sea of delocalized electrons surrounding positive metal ions.
Which explains why metals conduct electricity and heat so well.
Exactly, those mobile electrons. Metals are also usually strong, dense, malleable, ductile. That iridium density calculation, work example 12.5, shows just how dense metals can be, reinforcing that common sense check the AI promotes.
Got it. So 4 types: ionic, covalent, molecular, metallic, defined by their bonding.
And the AI's job is to help the professor guide students through connecting the bonding type to the observed properties.
Okay, almost there. What about the transitions between phases?
Phase changes, right?
Yeah.
We have solids, liquids, gases, those are phases. Moving between them involves energy changes.
Melting, freezing, boiling.
Vaporization, condensation, sublimation, solid to gas, deposition, gas to solid. 6 total.
And each has an energy associated with it, like heat of fusion for melting.
Molar heat of fusion, FLAFUS. Molar heat of vaporization, FLAFUS. Molar heat of sublimation, FUSIB. And interestingly, SOFIT is just office plus HFAP. Energy is conserved.
Hess's law again. Okay, this feels really relevant. You mentioned steam burns earlier.
Yes. A key real-world connection the AI would emphasize. Steam at 100 degrees C transfers way more energy than water at 100 degrees C because it first has to release all that HFAP energy just to condense into water at 100 degrees C before it even starts cooling down.
Ouch. And the snow example?
Right. Eating snow forces your body to supply the aphids to melt it, which uses up precious body heat, making you colder. A critical survival point derived directly from phase change energetics.
These are great examples the AI could suggest to make the concept stick.
Definitely. Heating curves also show this visually. Temperature stays flat during melting or boiling because the added energy is breaking IMFs, not raising kinetic energy. And HFAP is usually bigger than APHIS.
Why is that?
It takes more energy to completely separate molecules into a gas than just to loosen them up into a liquid. We also see concepts like critical temperature and pressure on these diagrams, leading to supercritical fluids.
Okay, and the big picture is the phase diagram.
The phase diagram, yeah. It's a map showing which phase is stable at any given temperature and pressure.
Yeah.
You have lines separating the phases and points where lines meet.
Like the triple point.
The triple point, where solid, liquid, and gas all coexist in equilibrium. And the critical point, beyond which you just have a supercritical fluid.
The AI would probably use CO2 and water as key examples.
Absolutely. CO2's triple point is above 1 at atom, explaining why dry ice sublimes normally.
Yeah.
Water's diagram is weak.
That negative slope.
That negative slope for the solid-liquid line, it means applying pressure to ice can melt it. Most substances solidify under pressure.
And that's why ice skating works. The pressure melts the ice.
Creates a thin lubricating layer of water under the blade. It's a fantastic tangible consequence of water's unique phase diagram, a perfect aha moment the AI would flag for teaching.
And interpreting these diagrams, like worked example 12.7, is a key skill.
Definitely. Reading the state, predicting phase changes with changing T or P, practical application.
Wow. Okay, so we've gone from tiny intermolecular forces all the way up to why skates glide on ice, all viewed through how this specialized AI could help teach it better.
It really shows how interconnected these concepts are, and how an AI, focused on conceptual understanding and anticipating student hurdles, could be a powerful tool for an instructor. It's about building that strong foundation, that intuition for why things happen chemically, before getting lost in the math sometimes.
So what does this all mean for you listening? Well, even though this AI is for a professor, the way it breaks things down, core ideas, common confusion, real-world links, that's exactly what we tried to do today for your understanding of liquids and solids. Maybe the next time you see ice floating or steam rising, you'll think about those invisible forces, the energy-changing hands. And maybe, just maybe, you'll wonder, what other everyday things are just waiting for their own deep dive?